All right, so far we've learned two rules. We've learned the constant rule and we've learned the power rule. Yeah, I guess you could say three rules because we split up that x, the derivative of x, into its own. So let's say we've learned three rules. Hopefully you have those written down, you have those memorized, you have them on note cards or something like that to help you practice so that you know those rules and you can apply those rules, because we're going to add to that list here right now. There are a few other rules to help us find derivatives. One of them looks like this first one, where if we have a number, c, and it's multiplied by our function. For example, if I give you this equation here, y equals 2x cubed. You notice that there's a coefficient in the front. There's a 2. This 2, if it's just a number, we can actually leave out in the front and then just find the derivative of the rest of my function. So the rule looks like this. As long as it's just a number, we can leave that number alone and then find the derivative of the rest of my function in order to be able to find the derivative of the whole equation. So for example, this 2x cubed, if I want to find the derivative, I can leave the 2 out in front as long as it's just a number being multiplied, and then I can find the derivative of x cubed. Using my power rule, I can say that my derivative of x cubed is 3x squared. I have a 2 times a 3x squared, or I can simplify and really say that I have a 6x squared. All right, the next rule says that I can find the derivative if I have a couple of different terms added or subtracted. If I have a whole bunch of different terms added or subtracted, a polynomial, I can find the derivative simply by finding the derivative of each little part. Now this only works if they're added or subtracted together. It does not work if you have a whole bunch of terms being multiplied together. We'll talk about that rule later. What it says is that you should be able to find the derivative of each little piece separately, as long as there's only a plus or minus sign in between. So I should be able to find the derivative of 4x to the 7th, and then I should be able to find the derivative of 3x cubed, and then just subtract those answers together for my derivative. All right, let's apply these rules, practice these rules, so that we get the hang of it. If you look at example number 3, it says here if y equals 8x to the 4th, and we want to find dy over dx. We want to find the derivative of y. You might notice that we have a coefficient of an 8. It's just a number being multiplied by my function. So I should be able to take the derivative by just leaving that number out in front, the 8, and find the derivative of the rest of my function, x to the 4th. Using my power rule, I can bring the 4 forward, and I can subtract 1 from the exponent. So the derivative of x to the 4th is 4x cubed. Let's go ahead and simplify that answer by taking the 8 times the 4 and really saying that my derivative is really 32x cubed. Now you might want to do that process slowly, but eventually you might see that instead of rewriting the 8 and then multiplying it by 4 later, you can actually take this 4 and just multiply it by the 8 right away and get 32x, and then subtract 1 from your exponent to get that cubed. All right, it might not be as obvious though to pick out that there is a coefficient on our function. Look at b. b says we have y equals negative 3x to the 12th over 4, and we want to find dy over dx, the derivative. This looks a little bit funky, right? We don't have problems where we have division. We don't know how to take derivatives of division problems yet. So we must have to rewrite this problem into a rule that we do know. Well, if we have a coefficient and a denominator that just has a number in it, we can actually rewrite this as a coefficient to our function. So really, 3x to the 12th over 4 is the same thing as negative 3/4 times x to the 12th. So instead of writing it as one fraction, we can actually separate it into two pieces that are just being multiplied together, right? It's the same thing as my original problem, just kind of separated a little bit, so it's a little easier to see that there is a negative 3/4 as a coefficient. And now it's not a division problem, now it's just a problem that has a number in front. And since that negative 3/4 is just a number in front, I can find the derivative by leaving that negative 3/4 in front, and then just finding the derivative of the rest of my problem, the x to the 12th. Bringing the 12 forward and subtracting 1 from my exponent, I get 12x to the 11th, that I'm just going to simply multiply by my negative 3/4. Multiplying the tops with tops and bottoms with bottoms, I get negative 36 over 4, which can be reduced to negative 9x to the 11th. So the derivative of that problem would be negative 9x to the 11th, being able to recognize that really this negative 3 over 4 is just a coefficient that I can bring to the front. Okay? All right, look at C with me. C says that I have a function 2 over t, and we want to find the derivative. Now again, we don't know how to find derivatives of division problems. We only know constant rule, power rule, we know the rule if there's a number in front, and then we know a rule if our terms are added or subtracted together. But we don't have a rule where we have a variable in the denominator. So I need you to rewrite this problem so that it looks like one of the rules that we do know. Well, this t really is t to the first in the denominator, right? And we should be able to bring that t up to the numerator next to my 2 and call it 2 times t to the negative 1. When I bring it up to the top, it makes that exponent negative. Now I can find the derivative. I can leave the 2 alone if I want to, and then I can find the derivative of the rest of my function, the t to the negative 1, bringing that negative 1 forward and subtracting 1 to the exponent. I ended up getting negative 2 t to the negative 2. I want to make sure that all my exponents are positive, so let's take this t to the negative 2 and drop it down to the denominator. So the derivative of 2 over t is really negative 2 over t squared. All right, look at D. D has a function 10p to the 2/3. We have a 10, a coefficient, that we can leave alone. Then I can just find the derivative of the rest of my stuff. I can bring the 2/3 forward, and then I can subtract 1 from the exponent, or subtract a 3/3, which is really 1 just with a common denominator. When I do that, I have the 10 coefficient, I have the 2/3 that I brought forward. When I take 2/3 minus 3/3, I end up getting a negative 1/3. Let's multiply across the tops of those fractions and the bottoms so I can combine these coefficients here. I ended up getting a 20, that's my 10 times 2, over 3. And then I had this p to the negative 1/3 that I wanted to make positive exponent, so I dropped it down to the bottom. That means I have a 20 in my numerator and a 3p to the 1/3 in my denominator, using that rule where we have a coefficient. All right, let's do a few more here. Look at E. E gives us a function 3 times the square root of x, and we want to find f prime. We want to find the derivative of f. But remember, we don't have a rule that has radicals in it. So I need you to take this 3 times the square root of x and rewrite it for me. Do you remember that we can rewrite radicals as rational exponents? So instead of calling it 3 times the square root of x, I can call this 3 times x to the 1/2. Now I have a 3, that's a coefficient. It's just a number, so I can leave it alone. And then I can find the derivative of my x to the 1/2. I can bring my 1/2 forward and subtract 1 from the exponent. So my new exponent is negative 1/2. On my fraction, if I put this 3 over 1, I really have a 3 over 2 times x to the negative 1/2. But let's take that x to the negative 1/2 and drop it down to the denominator next to my 2 so it becomes positive. So we can say that the derivative of 3 times the square root of x is really 3 over 2x to the 1/2. Or if you put it back into a radical, you could really say 3 over 2 times rad x. All right, one more. If f of t is equal to negative 8t, and we want to find the derivative. Well, I have a negative 8, that's a coefficient, and then I have t, or can I really say t to the first? And so if I use my power rule here, if I leave the negative 8, and I use my power rule to bring forward my exponent, and then subtract 1 from my exponent, 1 minus 1 is really 0, right? All right. But what is anything to the 0 power? What is t to the 0 power? Well, hopefully you remember that anything to the 0 power is just 1. So what I really have is negative 8 times 1, which is really just negative 8. So the derivative of negative 8t is just negative 8. All right, let's see if we can get through example number 4 in this video as well, so that we can see, actually I'll make a new video for example number 4. That was a lot to process. So practice some of those ones in example number 3, and then we'll do a new video for example number 4.